Okay, welcome. This is David Whiting from H2O. We will be starting in about a minute. While we're waiting, please create an account for yourself on Aquarium and go ahead and log in. We'll be using the chat function of Zoom in order to ask questions. Okay, it looks like it's time. Let me start my video for just a second here, and hopefully you can see me. My name is David Whiting. I am the head of training at H2O and a data scientist, and really excited to be here and be able to show you driverless AI version 1.9, and we're going to try to cover a lot of things in the next hour. We have additional trainings available, and so in the chat you'll see a link for where you can sign up for those trainings. Today, I apologize, but we're going to be running through things fairly quickly in order to keep up. So now, and let me stop my video for a minute. Now, if you'll go ahead and log into aquarium.h2o.ai and then click on this thing called Browse Labs. I have a few more buttons than others will have. We have a number of different labs. We'll talk at the end about how we use this for training. But if you'll come down towards the bottom to this one that says AI for Driverless AI Training, and go ahead and click that. And it looks like we have a number of participants today. For most of you, hopefully when you come here, click Start Lab and then click your link. For a couple of you, it may take a minute or two. We basically created 60 of these instances in the cloud so that everyone can jump on and use driverless AI. So let me pause here for just a minute and allow everyone to get onto driverless AI. Like we mentioned before, this is version 1.9.0. There are a number of tabs across the top: projects, data sets, AutoViz experiments, etc. We'll get a chance to preview those as we go through. And this lands you in the data sets tab. So hopefully others are able to get here as well. While you are, let me show you, we have some preloaded data here. We've got some data from a lending club data set, data from credit card data set. These have both been extensively used in Kaggle elsewhere, and we'll use them. Let me show you how to load data really quickly. Up here in the yellow, you can click Add Data Set. You can upload a file, connect to Amazon S3, etc. Let me click on File System really quickly to show you this is your own AWS file system. So you would come to Data, and then down to Training, and here are a number of different data sets that one could upload. And for instance, if we were to upload the Lending Club data set, I would click on that, click to import it. It's going to actually tell me that that's already been imported. So let's not import the data again. So the data import is very easy. We've got a number of connections. Let me just catch up on the chat really quick and make sure I haven't missed anything. Okay, if you're not able to log in, please chat. Please send a message on chat so that we can keep up. So we've got a lending club data set, credit card data set. Let's start with this credit card data set, and where you see it say click for actions, we can click here and very quickly look at details. And this just gives me a summary of the different columns in the credit card data set. What we're going to use this data set for is I want to determine who's going to default on their next month's credit card payment. So they're going to miss their next month's credit card payment. I have some payment history for them for the past 6 months. That's what the 1 through 6 refers to here. I have the amount that they were billed for the last 6 months. And then this status refers to behavior. Did they pay on time or not? Anything 0 or less is good behavior, someone paid on time, and positive values indicate how many months late they were. So this just very quickly gives me some reference information on my data. If I want to see what my data set looks like in an Excel spreadsheet form, I can click on that button up here, which changes now to data set overview. So just very quickly, that's how we would look at data before we're ready to model. So the next thing I want to point to here is, let's go ahead and click on visualize. And so visualizations, one of the things that is really nice about driverless AI is we create a whole bunch of and in some cases interactive visualizations for you, showing you important features of the data that one would want to use in modeling. So for instance, for this data set, there are 3 correlated scatter plots that are important enough, or basically have a high enough correlation coefficient, that you should even bother looking at them. And the other, there are approximately 190 possible scatter plots for this data. We're only showing you 3 because they're the only ones that are relevant. So we do some filtering and sorting for you. For instance, this is one of my favorites, an outlier plot. And the idea behind an outlier plot, by the way, if you need help, you can click on the help and it will tell you everything you need to know, including references to the literature if you're unfamiliar with anything. But it includes basically a histogram here of any values that would have outliers, of any columns that would have outliers. And within this, it also includes some dots, right? And these dots are anomalous or outlier points. We can click on this dot and it will take me to the actual data value so that I can inspect that. And again, the reason for, so we're not showing you every variable, we're only showing you the ones that have outliers, and this is a good way for the data scientist or the modeler to get a really quick idea of whether those outliers are actually true data values or not, right? There are a number of other things that, that one can look at within visualizations, but these AutoViz all live under this AutoViz tab, that next tab, and you can do that per data set to get some insight about the data sets. There's a lot more that we cover there in our training, and I'm going to skip that for the moment so that we can move on to prediction. Now, very quickly, we've done the visualization, the split. I'm going to skip the split functionality. That's how we split data into a train and test, and it's fairly straightforward. Let's go to predict, because that's what we want to do, is build a predictive model, build a really fabulous supervised learning predictive model. But to do that, let me start with my training data. So I'm going to come up here to where it says card train. I'm going to click somewhere on the line and say predict. And this brings me to a new view. Well, first it's going to ask if you want a tour. For the time being, say no. We have the data set that we picked, card train. You want to make sure this is the correct data set. There's the training data set. Click on the test data set, and let's include the card test data as well. You always want a test data set to evaluate your work on data that hasn't been used in building the model. And then let's pick our target column. So we're going to have to scroll down, and we'll pick default here. Then we get some spinning wheels, and a bunch of stuff happens here. And there's a lot of detail here, but basically each one of these, we have 3 different dials or knobs here that can go from a 1 to a 10. And as I dial this knob called accuracy down to a 3, you'll see on the left-hand side that I get a sense as to what's happening, what these knobs are doing. So basically, I have out of the box 10 times 10 times 10. I've got 1,000 different recipes that we can run right off the bat. Really quickly, this accuracy knob adjusts how we're doing feature discovery for our feature evolution, and it adjusts what my final model is going to look like, whether it's an ensemble, whether it's one model. We call it a pipeline because that includes all of the feature evolution along with the model. So that's accuracy's main role. And as I crank accuracy higher, we're going to see changes in that feature evolution, the way we do discovery. To ensure that we get done fairly quickly, I'm going to move accuracy down to like a 3 or a 2 or something. Time. So under the hood, one of the things that's happening here is we are allowing the models and features to evolve. And these features will evolve sort of in an evolutionary sense, survival of the fittest. And so as you crank time up higher, that's going to allow more time for evolution. We have early stopping rules on all of our evolution. And for right now, again, I'm going to move this down to maybe a 2. And then at a really high level, interpretability is going to help determine what kind of models I build and what kind of features I'm allowed to have in there. So we can think of, as interpretability goes higher, it's going to be easier to explain what you've done or the kind of model that's been built to someone like a regulator or to a business partner. As I go lower, the complexity increases. So interpretability of 1 will throw sort of everything at it with no constraints. So let's move this up to a 6 or a 7. And from here, let's go ahead and launch the experiment. And what you're going to note at the beginning, so here's the experiment, and the experiment is basically the model build, model fit process. But this model build, model fit process is, let's see, as we get going, we're going to be looking at a number of different models as they're being built and a number of different features as those features are being created. At the outset, we begin with some distributional checks to make sure that the training data set and the test data set have similar distributions within the columns, the factors we're looking at. And you'll notice here that we've just built our first model. Turns out that it's a light GBM with 22 features. And as we go on, we're going to continue to build other models. The idea here is we want to maximize the criteria we're using is the area under the ROC curve. We want to maximize that. Occasionally we try a model that didn't do so well. So the GLM in this case didn't do nearly as well as the equivalent light GBM. And so we're going to allow this to evolve. So in some ways, this is in a fairly kind of black box sense. We haven't done much to adjust what driverless AI is doing other than turning moving knobs up and down. While this is running, right, and while it's trying to create a better model, I've got this notifications here I can hit. And notifications tells me things about the data, like, okay, that we've discovered the data are slightly imbalanced. Here's the target class fractions, so its imbalance is 1 to 3.5. Driverless AI has automatically dropped some columns, automatically dropped an ID column. And if that's not what you wanted to have happen, we show you how to fix that so that if that's unintended, you can go back. It's also telling us, so this notifications is going to tell us things as the experiment is going on. It looks like we had some early stopping take place here. So while this is going, this is all sitting inside this experiments tab, right? I've just started building an experiment. I probably should have named it something, but I didn't. If you come to the far right side, there are 3 dots here. And if I click the 3 dots, let's click on new model with same parameters. And this is how we often go to the next model after building the first. It pre-fills everything the same way I had it initially. right? It's pre-filled my test data set, what my target column was. I can come and move some of these around, but let's dive into expert settings quickly. So this is where, if you're a data scientist, this is where the meat is. There's a lot of really nice things that we can do here. So for instance, these are all settings about the experiment space itself, right? Here are settings that are the model. And so you'll notice we have a number of models that are run by default. If we leave the model setting at auto, that means I'm going to let driverless AI decide based on data and other things whether to include it. If I want to force a model to be included, I can turn on GLM. I can turn on XGBoost. Maybe for whatever reason, I don't want TensorFlow, and maybe I can't use light GBM in my company because that's not allowed. So I can leave some things on auto. I can explicitly turn things on or turn them off. This gives me quite a bit of control and a lot of other features, including things like if I've got imbalanced data, I can come down here and tell it what type of strategy I want to use for imbalanced data. So, oops, I'm sorry, let me go back to expert settings. So there's a lot of things within model that we can do to fine tune this. In terms of feature evolution, right? Our default feature engineering effort is at a 5. I can turn that completely off by moving it to a 0. I can turn that up, moving to a 10. So we'll do different feature engineering as we go on. We have an automatic leakage detection that you may want to be able to turn on, and there are some settings revolving around that. Some specific settings for time series and NLP and image, but let me show you recipes. This is where things really get fun and interesting. So for instance, here are the transformers. When I click on include specific transformers, all the ones in yellow here are ones that come pre-packaged with driverless AI. And so perhaps there are some transformers that you don't want to use, or by regulatory reasons you can't use. You have the ability to come through and turn these on or off. All of these are documented. So you've got complete control over what transformers driverless AI is going to try while we're evolving. Likewise, I've got another one for specific models. This is another place that at a very high level, I can turn on or off models. So for instance, if I want to uncheck all the models and only allow generalized linear models and light GBM, and I don't know, let's do an XGBoost GBM. Now, as I save this, right, I get a chance to come back, and you'll see that the recipe has changed, and it will include only the things that I'm allowing. And then I can go ahead and launch a new experiment, and we'll let another experiment run. Well, let me introduce you as we go to the experiments level here. You'll see that there are a whole bunch of different experiments. In fact, we've got 3 pages of experiments that have been pre-run. And under each of, and this can get kind of confusing when you're working with a lot of different data sets. So we have this tab called projects. And if you come into projects, let's come to credit card default. These are all data sets dealing with where we've tried different things, different settings, and we want to see how well they've done. You'll notice we've got this validation score is an AUC. And so I can order these by validation score. But what I really want to do is order them by, let me come up here and select the scoring data set of card.test. And if I come over and select the scorer, and let's use AUC because that's what we started with. As I go ahead and do these, now you'll notice that if I sort by test score, the default one that driverless AI suggested actually turns out to do the best on that test data. monotonic does next, etc. So let's look at, and we've tried a number of different things here. So let's go ahead and look at, for instance, this one that we've called card monotonic. And the reason I've called it card monotonic is that when interpretability is a 7, we use monotonic XGBoost models. So let me show you in terms of projects. I'm sorry, let me do one thing here. Let's compare 2 or 3 of our best models. And I'm going to use this one that I called Card Big, which had some high settings and took me an hour to fit, versus Card Monotonic and Card Default. And let's click on compare these 3 items. And you'll notice that we've got a summary at the end of the day on each of these models. And along with a summary, we have this information is on the validation or the cross-validation data. So I've got my ROC curve for each of these models that I'm looking at, et cetera. If we come to the top here, you'll notice, for instance, that here is Card Big is one where I made those dials go from to 867 from 546. And you'll notice that with Card Big, where I set that up, that we created some more than 1,500 features were tried, automatically created. At the end of the day, 43 of those were selected. We actually created 161 models for our feature tuning. We created 825 models for feature evolution, as opposed to 45 models over here and 18 models. So part of what those settings do is how much engineering we're going to allow driverless AI to do for us under the hood. So we get a chance to compare models. We can also compare within the models the features that were created from these models. So let's look at a model in particular. Let's come to Card Default. And once more, let me pause and look at the chat just for a second. I apologize for rushing through this very quickly. There's just a lot to cover, and we have additional training that we're more than happy to offer. So once we're at this point where the model is done, let's click on Interpret this model. And as I click on Interpret this model, I come to an area that we call MLI for machine learning interpretability. So I have 3 things over here. On the left-hand side, I've got a summary, and the summary goes into some detail and is maybe not the best place to start. I have information on the driverless AI model, and then I have information on my surrogate model. So if you're familiar with LIME, we can talk about K-LIME, decision trees, feature importance, loco models. But let me start with the dashboard, because this is really a nice place to begin in looking at a model. The idea behind this dashboard right now is that I have on this upper right-hand corner, I have my feature importance, and it turns out that for this model, right, these features, by the way, are all in terms of the original variables. For this model, status 1, which we ran very quickly through this was, did you pay your bill on time last month or not? Status 1 turned out to be the most important variable in predicting whether someone would default. And if we come down to the corresponding partial dependence plot here, we can, and this by default goes to the partial dependence plot of that status 1 variable. We'll see that I'd mentioned before that anything less than 0 was good customer behavior. So someone's probability of default is right around 20%. If they missed their last month's payment, then their probability of default goes up to 46%. So that's the largest jump here. In terms of, so that's what's happening on the right-hand side. On the left-hand side, we have a surrogate decision tree that is built on top of our predictions. So the idea with surrogates is that my Y variables are the predictions of my black box model, of this model that we've just produced. And if you'll notice here, I have, and in fact, I'm going to move back from the dashboard. So let me close the dashboard out so I can look at these individually. In my surrogate model, I can look at my feature importance values, and here they are all. And you'll notice that status or behavior turned out to be the most important. Bill amount was next, and credit limit, payment amount, etc. So, and you can scroll all the way through to see how all of the variables were impacted. So there's my feature importance. In looking at partial dependence plots, I can choose which variable I'm looking at. So we looked at status 1. Let's see what happens with status 2. Status 2, we get a bit of a jump if you're 1 month late or 2 months late, 2 months ago, in making your payment. Right? So this partial dependence plot allows us to investigate what's happening, and I'm sure everyone here is familiar with feature importance and partial dependence plots. We've mentioned the decision tree. The decision tree is a good way to understand what the model is thinking, right? So this is a way for you to interrogate the driverless AI or your black box model, and we'll see that, okay, if status 1 is 1, then I come down and the next thing I do is check my status 2 values, right? And if my status 2 value is high, then I'm going to check status 5. So it's basically saying I look at your behavior last month, then I look at your behavior 2 months ago, and you'll notice as we follow down through this, you end up with basically a cluster or a grouping of observations that are that have very high probability of defaulting versus, on the other end, those that have low probabilities of defaulting. So this is how the model is thinking about, this is how the model is dealing with the data. Very quickly, Lime is a local linear model, which basically gives us a chance as we look at the Lime values here. This gives us a chance to understand how well my model is predicting. And as I click on any of these values, I get what we call reason codes. So if you're in regulated industry and you need explanations for, so for instance, if someone's applying for a loan and you turn them down, you're required by law to explain why they were turned down for a loan. And this is, using Lime, one of the ways that we derive these reason codes. So again, very quickly, and I apologize for moving so fast, the thing that's going to increase my probability of default the most is if status 1 is 1. And the increase of that is 0.21 increase. If status 5 is 5, if 5 months ago we still haven't received your payment, that's also going to increase, etc. But I can also get down to actually a local reason code that is tuned to this specific individual. So this gives us the ability to create these reason codes immediately. Let me quickly show you the driverless AI model. And this shows, for those of you that know Shapley or have dealt with Shapley, Shapley values are a great way to decompose a prediction. And this gives us our equivalent Shapley, and you can paginate through the Shapley values all the way down, you'll notice that the yellow here are the global, and the gray is the individual Shapley for this individual. So if I get rid of this and I say globally, let me clear that. Here's globally, according to Shapley, status 1 is the most important variable, but then credit limit is the next most important after in terms of how Shapley looks at importance of variables or their contribution to the prediction. Then when I added an individual in here, like 1, 2, 3, I can look at the Shapley value actually for that individual and see how each of these features contributed to the prediction for that individual. And in this way, have a way to check my model. So that's a very quick, so I should note, this is the straightforward Shapley. We call it naive Shapley. The transformed Shapley shows you the Shapley in terms of the variables, the feature transformations that we created under the hood. Similarly, we've got feature importance in terms of the original features. And this actually looks very similar to what we just saw with Shapley in terms of the original features. In terms of the transformed features, here's the feature importance there. So we actually do, in addition, some additional training on MLI, and all of the MLIs sit here under this MLI tab. And so you can see for a number of different models, you can investigate in great detail what those models have done. So let's come back to our credit card project. I'm going to come to credit card default project. And once more, apologize for continuing on and not taking much of a breath here. We created a couple of new experiments. Let's link them in here. So I'm going to link. I clicked link, and I'm going to link this first experiment, and that goes into my leaderboard. As I want to compare things, I'm going to link the next experiment. So I have a couple of experiments here. I can go ahead and score those two on the card test data and the AUC to see how well they did compared with my other models. And once the scoring is done here, so these will run for a minute here. Once it's done, we can go ahead and view the score in diagnostics. So one of the things that comes out, and by the way, this sits under this diagnostics tab. One of the things that comes out at the end of the day is, regardless of what diagnostic you want, we provide a lot of different diagnostics through this. This is based on a data set that has not been used to fit the model. And so if you prefer an ROC curve, or if you want to look at a lift chart, we make all of these available for you to download and include yourself. So that falls under that diagnostics head. Once more, let's come back to projects. Let's come to, let's come to the project that, let's go to experiments. And let's go to an experiment. This is an experiment that just finished. And let me see, I was having a problem with my computer today. This is an experiment that ran very quickly. I was having a problem downloading the auto report. Let's see if the auto report works here. Yes, the auto report works on this model. So if you've built a model, you can download the auto report. I just wanted to show you one of the features, one of the things that we do at H2O is try to make the life of the modeler as easy as possible by, excuse me, I'm trying to move this and it wants me to do something else. Here we go. We try to make your life as easy as possible as a modeler by automatically documenting everything we've done. So every experiment is created with a document under the hood, right? And these basically a white paper that with very little additional help, you could move into a white paper. So here's a case that, maybe we don't like this one so much. Hey, when I built the ensemble at the end, it looked like my performance went down. There may be multiple reasons for that. One of the things that's really nice here is, as we mentioned, all of those different transformers that we used earlier, and you may say, wow, I don't know what those transformers mean. Here are we include from the documentation, basically in your white paper, the documentation of all the transformers that were tried with this experiment. And so it goes through a number of them. And then it looks like in this particular experiment, yeah, we had a couple of transformers. A lot of them are based on original data. So here's how the transformers actually showed up in the experiment. And we had a couple kind of come out at the very end. And that's because we didn't spend much time doing feature evolution here. We did a very quick experiment. But notice that not only have we given you so this is a cross-validated target encoding. You can come up here and look at the cross-validated target encoding, which is one of the, here we go, cross-validated target encode transformer, explains what that transformer is doing. Here we give you the settings for that transformer, what columns it was used on, give you some internal parameters that were used in creating that target encoding. So first off, very quickly, we have, this shows all of the things that went into the light GBM model that we used here at the end to do predictions. The documentation here is really nice because this happens with how many pages? We've got 39 pages of documentation written just for this one quick model that we built. So that happens everywhere. Now, to get to my last point of the features, we give you we tell you what the feature engineering recipe was, so what the transformer was. I can also come up here and say, well, I could score another data set. And what score another data set means is we start with the same raw data. So I'm going to start with the same 25 columns or 24 columns because I'm removing my Y variable. If I start with the same 24 columns and feed it into driverless AI, we'll end up with the scores, the predictions. Is it, did someone default or not, right? And the probability of that. What the transform another data set does is it starts from this space with those 24 original columns, and it will output in the transformed space. So if you wanted to, if we went ahead and did the transform another data set, and we transformed from our card train, you could see numerically what those transformations were. So that's very useful as you're going through and working on things. Let me also show you a really quick deployment here. So we have a number of, I'll call them one-click deployments. This is a way to actually take this model that you've created and perhaps spent some time doing diagnostics on and looking at MLI to understand what the model did and be able to score off it immediately. So there are a couple of different approaches. If you use Amazon, we can publish that immediately to an Amazon Lambda function. Let's go ahead and deploy this, and we're going to deploy this to a local server, which is going to sit on your instance. So if I click deploy, the thing that's neat about this is it goes from, this is going to take us maybe 60 seconds or less. I'll be able to go from having a model that I've written the code for, if you think of modeling in Python and then having to rewrite everything in Java, for instance, so that it works on a production system. This deploys behind a REST server in a production type environment. And so even though this is an example of deploying on your own EC2 instance, it's very easy to deploy this elsewhere. Deployment, when we're using driverless AI, uses an object that we call a mojo. And basically that is a a binary artifact that contains all of the feature transformations in the experiment, the latency, so how quickly that can score. We'll return and look at that in just a second. But hang tight while we deploy your model. This deployment, there we go. Our model here has been deployed. You could go ahead if you wanted to and copy this code. And all you have to do, and I don't have time to do this live for you right now, all you have to do is change this local host, because this is being deployed local to your EC2 instance, to whatever your EC2 instance address is, and you'd be able to go ahead and score this model immediately. So now I've also got a deployment that is independent of driverless AI. And let's come down here really quickly. And I don't know if you can see here, but this is the Mojo latency basically tells me how quickly I can score each of these in that deployment. So it's how quickly that can do it. And we're at under 0.05 milliseconds, right? So this is much faster than your typical kind of Python scoring. This can support things like real-time scoring, etc. That's also available if you click here on download Mojo scoring pipeline. This automatically implemented Mojos. This download Mojo scoring pipeline will allow you to call this thing from Python if you're a Python person, or if you're an R person. You can call that object directly from R. A very quick way to go into deployment. You can use this if you want to use Shiny. You can use this if you've got a Python front end and you want it to score very quickly. This is a suggested way, or you can call it from Java. So I've had a chance to show you some stuff in the last about 10 or 15 minutes. Let me talk about recipes. And we did recipes a little bit, but we didn't do it justice. I did sort of a flyby. So let's come back to experiments. And let's come here to, well, let me come down to this one I called card default, so that we're all starting at the same place. I can come to card default. Let's say new model with same parameters. And as we go into expert settings, you'll notice across the top, there's this thing called load custom recipes from URL, or upload custom recipe. And in official recipes, external, this is a GitHub site where we've curated these recipes. Now, what is a recipe? A recipe is basically Python code that you can integrate into driverless AI's functionality. And there's a lot of nice things about this. If you want to actually completely customize what driverless AI does, so for instance, let me do something that will happen quickly. We can look at recipes for models. I'll go to models, algorithms, cat boost. If you wanted to include, and I've already included cat boost in this, but if you're familiar with the cat boost algorithm and wonder how that would work, you can go ahead. We click raw here. We would copy and paste this into load custom recipe from URL and paste the recipe in, and we do a save. And as it's starting to load this, it's basically doing behind the scenes, it's doing like a pip install, and it's going to do a bunch of tests, etc. Because of time, let me just go ahead and abort this so that we don't continue doing that. But let me load something that may load a little bit quicker. So I have a bunch of different options around models. So if your favorite model has just been developed, if you've created your own internal code in your business and you wish that you could use that, we have instructions on how to build your own recipes, or you can use some of the recipes we've created. So you can use the random forest implementation that comes with scikit-learn, for instance. You can use the extra trees. We've got cat boost, which is a wrapper for the cat boost algorithm, which has become very popular recently. I can also include additional transformers. So, and transformers in a lot of different areas. In NLP, for instance, if you're familiar with NLP and you're doing an NLP problem and you'd like to use something from a package called text blob, this is basically pulling in, this is a very nice recipe because it's simple to follow, but it's pulling in one function from this package called text blob so that we can use it in our feature transformations of a new experiment. The other one that's really nice is in scorers. So for instance, let's go to scorers, classification, binary, and I'm gonna pull one out. This is an oversimplified one, but it's a cost-based scorer. So I'll explain what I mean by oversimplified. The nice thing about a cost-based scorer is if you actually know the cost of your false positives and your false negatives and you want to put them out there, then instead of having to translate an AUC value into some kind of numeric cost, this does it directly for you. So let's use this as an example. And by the way, I said this is a little bit naive because the threshold we'd actually want to tune, so we can talk about how to do that in the future if you're interested. You're going to want to change those false positives and false negative costs to reflect what you're really doing. But this is really nice because it follows what you've probably learned when you've done cost-based metrics. So let's click on raw here, and we'll copy this, and just to show you how to add that to a recipe, I'll load that recipe from the URL. We'll click save. And as it's saving those, I can actually come back into my recipes, look at the scorers, and remember we showed all the scorers we had before, and there's a new one here called cost. And so I've just added my own scorer so that if I want to rerun, let's say I'm going to save this, very simple example. If I wanted to rerun this using a cost scorer, and once more, let me make these go small so we go fairly quickly. I can launch this experiment. And now what you're going to see come up on the left-hand side is a cost metric, even though we're going to still show you the AUC and other information on the right-hand side. So let's give this just a second. Actually, let's return to this in just a second. I noticed that we're short on time. There is one more thing I wanted to show you. Let me see if yeah, so this is the only experiment I've got running. Sorry, let me see if we've gotten anywhere on it, if our first model has shown up yet. I also wanted to show you what we call the leaderboard. So here we go, we've tuned, our first model should be showing up in just a second. Here we go. So based on that, 68.36 is the cost per subject on that person. Obviously, we want to minimize the cost as we go across here. And so now I have something that's directly in dollars and cents. And it looks like we didn't do so well in this. My settings were probably too low. So instead of optimizing AUC, I quickly optimize something based on cost. And this cost metric is something that's directly interpretable. This, by the way, is really good to use if you're doing things like fraud, which are also rare event models with imbalanced data, because then you can put the cost of your false positives and false negatives to reflect what you've really got. Let me finish this. Let me just abort this really quickly. So we've got just one more second to let's come to data sets once more, come to this card train, click on predict very quickly, click on test data set like I did before, click on select target column as default. And I know I've run through this very quickly, move these down a little bit. And then there's this thing called create leaderboard. Now you can manually create your own leaderboard, but the nice thing about this create leaderboard is it will create a number of different experiments that will give you a good overview of your model and a good place to start. So I may have jammed up my system here by going a little too quickly while my experiment was still running. Let's give it a second. Okay, so here is the leaderboard, and it's going to start fitting each of these models one by one. The first model has settings 1, 1, 10, and it's just going to do a few features to give us a real quick baseline, right? And then we're going to do a simple like GBM. We're going to do a constant baseline. So we're going to do a few simple going to slightly more and more complex models. If you want to, we've got just a minute or two left. If you come to projects, we've just created this new project. That is the credit card leaderboard. But you can come here to this lending club leaderboard. So we did it for a different data set. I apologize for kind of mixing messages here with a different data set. Select the scoring data set once more, select the scorer. And I think we used log loss. And you can see that now I've got sort of a nice starting place for me to start honing in on what models I may want to build. So if we were to take these from the best to the worst, we've got that constant baseline, we've got a single, this is a follow the regularized leader model that's been done with these. So this is basically a way to very quickly do a whole bunch of runs and maybe hone in on a modeling strategy. Now that being said, one of the things that you'll see here, and this is new in our 1.9.0 version, is that we'll stack up a bunch of these models to be run next. And when these are done, the next one in the queue goes and the GPU is available. So anyway, I have been talking pretty nonstop for about an hour. I've shown you an awful lot. I apologize for kind of rushing through this. One of the things I would say as a user of Driverless AI, who also does a lot of these courses and teaches an awful lot, is this is a great way to make a data scientist very, very productive, most especially if what you're doing is discovery on the feature engineering approach. So you can go all the way from beginning to production very smoothly, fully documented, etc. So that being said, it's now, we've got about 1 minute or so left. Hopefully we've shown you diagnostics, we've shown you MLI, we had a chance to show you one deployment. Resources, we have a lot of really great help. We've got tutorials baked in that you can walk through, very good tutorial site. The other thing you should know as a last message is that a majority of data scientists never use the UI that we've just used today to create experiments. If you program in Python, if you program in R, everything we've shown you today, you can do from Python and from R directly through those clients, just calling the same API that sits in the background that this UI sits on top of. So with that said, thank you. Hopefully all of you could hear me, and hopefully this was instructive, your first chance to be hands-on. Thank you for joining. This lab, by the way, will go away, but because you've got to log into Aquarium, feel free to come back. The the driverless AI training lab 1.9.0 will require you to log in a little bit more, but it has all the same material. So if you want to come back and play with it, come back to this lab number 4 and feel free to play with driverless AI as you're getting used to it. This is a service that we provide for you at H2O. So again, thank you very much for being here and for your attendance. And hopefully this has been helpful.